All right, so we're on 3.5C, rational functions. A rational function is one that can be written as a polynomial divided by a polynomial, okay? So it's just a polynomial divided by another polynomial. That's it, okay? A rational function may have one or more types of discontinuities. Okay, our first one that we're going to talk about is called a whole. So you can have a whole in your function, and that's called a removable discontinuity.
What is discontinuity?
It's what causes me to stop or break in my function. So our asymptotes are our discontinuities, right? Because we have to stop and restart, right? Okay, we can have a vertical asymptote. And a vertical asymptote is a non-removable discontinuity. Keyword here is non. Okay, and then lastly, a horizontal. So the difference between a reciprocal function and a rational function is you're not adding on a k value, okay? It is just simply one polynomial in the numerator and one polynomial in the denominator, okay? So I wrote a lot of it out for you so you wouldn't have to. So the first thing we're gonna look at is our two types of discontinuity. The first one is our removable, okay? And how do you know if you have a removable discontinuity? The way that you know if you have a removable discontinuity, basically what this is saying is if you factor the numerator and denominator, and they have a common factor, then that's where your removable discontinuity is.
I forgot what the factor was.
These are factors, the binomials. These are our factors. So notice here that each one has x minus 5, right? There's an x minus 5 in the numerator and an x minus 5 in the denominator. So I can remove them. Does that make sense? So I can remove them, which means that there's going to be a hole at x equals 5. Why is it at x equals 5? Because at x minus 5, which means x has to equal 5, right? That's where our removable lies. Yes, it was a hole because I removed it. Okay. All right. Next one is our non-removable. So our non-removable happens only if the degree, what is it? Oh, our non-removable happens only if in our denominator, we still have a factor or we still have a polynomial that can be set equal to 0. Okay, that's what's going to be the main thing. Main thing is if there is something left in the denominator, because our denominator can't do what? Be 0. Remember, your denominator can't be 0. It is okay for 0 to be in the numerator, but it is a no-go for the 0 to be in the denominator. Okay, that's where our asymptotes come from. That's how you get a vertical asymptote. So when we look at this rational function, we have x squared and x minus 3. Can I remove anything? No. So now I'm going to focus on x minus 3. What can x not be? So this cannot equal 0. 3. So therefore I have a vertical asymptote at x equals 3. And that's because x minus 3 equals 0. So x cannot equal 3. And is that what happens when we write a vertical asymptote? Yeah. We're saying what our x cannot be, right?
So what's that word?
Asymptote?
It's what it cannot be.
It's what it cannot be. That's where our imaginary boundary line would be. Okay. All right. Next is our what is this thing called? Uh-huh.
Is x equal 5?
We have a hole at 5. And that's because it was what? It was taking it out. If I can take it out, it creates a hole. If I can't take it out, it makes a what? A vertical asymptote. A hole is literally a hole in your graph. There's a space, a small, tiny space that will separate your graph. Yeah,
Oh,
it's a hole, like literally, there's a hole in my graph. Yeah.
oh.
Thank you. Someone caught it. All right. All right, here we go. So next it says, we're gonna let P equals the degree of the numerator and Q equal the degree of the denominator, okay? I think I changed that to M and N. So why did I switch it? I didn't change your notes completely. These should be M, N, N. My bad, guys. Yeah. Yeah. I thought I changed it all the way, but I didn't. I apologize. I'm sorry. All right. So how do you know if you have a horizontal asymptote? Okay, these are your rules. If the degree of your numerator is less than the degree of your numerator,
Miss, I wait, you should put M less than because those times I don't understand.
well, you write less than.
I've been in school, I don't know how long I still know what a less than versus sign is.
The one that almost looks like an L is less than.
I just do whatever this is eating, this is bigger number.
No, you see how this could almost be an L? That's your less than. M is less than N.
Oh, okay, it makes sense. So L go this way.
Yes, exactly. L's go that way. And then greater's the other way.
The big number.
Yes. Okay, so in this case, oh man, this is funny. If M is less than N, that means that the degree of your numerator is less than the degree of your denominator, then you have a horizontal asymptote and it's automatically at y equals 0. Okay, if your M is greater than your N, then what does it say? No horizontal asymptote. We will worry about what it means later in pre-cal. Okay, well, for algebra 2, we just got to worry about no. Okay, all right. The last rule is if M equals N, so if the degree of your numerator equals the degree of your denominator, then you have a horizontal asymptote at y equals A divided by B. And A and B are your coefficients, so just the numbers. Exactly. That's what this is. So this is an example of when that happens. So notice here, for here, my M equals, what's the degree of my numerator? 2. What's the degree of my denominator? 2. It's my highest power. Remember, your degree is your highest power. What is degree?
So if it was Q,
highest power.
so if
3. Yeah. And notice that M and N are the same. So all that's telling you is you're taking your leading coefficients and dividing them. What is the leading coefficient here? 4. What is the leading coefficient here? So your horizontal asymptote is at 4/7.
M and N equals highest power of a variable or any.
Of the variable, yeah.
So it's like 2 cubed, it could equal 3, which will equal.
It would be 3. It would be a third degree.
So the
Yeah.
M
Like, oh,
is
you
a-
said 2 cubed or x cubed?
2 cubed.
No, 2 cubed is 8. That's a number. Yeah, only the highest power of the variable. Okay? All right.
So the M is a big number, the N is a little number. The M is the big the big power in the.
M is your degree. Your highest,
The big degree. Is that
yes,
what M
the
is?
big degree.
And the N is a little degree.
No, it's still the big degree, but in the denominator.
Oh, okay.
Okay? That's why, shh, guys, degree of numerator, degree of denominator.
Still is the numerator. Okay, never mind.
Yes.
I just thought it was like overall, but. Yeah, okay.
So when we are looking for the discontinuities, we first want to factor the numerator and denominator completely. Look for the values that are zeros of both numerator and denominator. And if they exist, then that means we have a hole. If I can't remove anything, do I have a hole? No. Okay, then you want to look for the values of the zeros of the denominator. And that's where our vertical asymptotes are going to come from. And then we're going to check for a horizontal asymptote by comparing the degrees.
Okay.
Okay, it sounds like a lot, but once we do, you'll be like, oh, this is easy. Okay, do we really? What time is it? No, that clock just lies to me, so it scares me. Okay, no, we're not stopping. We got this. We can do it in 5 minutes. Okay, here we go. So our polynomial and the numerator, it has a degree of 2. Our polynomial on the denominator has a degree of also 2. Agreed? All right. Now we're going to factor them. The first thing we want to do you remember asking ourselves what multiplies to give me -6, but adds to give me 1? What multiplies to give me -6, but adds to give me 1? What kind of 3 and 2?
Oh,
There we go. Good job. A -2 and a +3. Those good old factoring skills. Okay. In the denominator, this is greatest common factor, right? What is the greatest common factor here? 3. So I can factor out a 3, and I'm left with -4. Okay. This is a special case. Anyone remember what this special case does? Anyone remember this special case for factoring? Difference of tables, really? Tables. Difference of tables. No, difference of 2 squares. Okay. What that means is that when you factor it, it can be factored again. So it becomes x -2 and x +2. Are those ringing any bells? A little bit of factoring. So we're fully factored. Okay, step 2. Is there anything that can be removed? Yes. What can be removed? X -2. So that tells me I have a what? A whole. And the whole is at 2. Good job. 3. Once you remove your whole, you're going to look and see what is left in your denominator. What do we have left in our denominator? 3 doesn't have a variable, so it doesn't matter. So what's the...
X +3 and X +2.
So this is just a number, but this is a factor. So we're left with x +2 = 0. So where's our vertical asymptote? At 2. Our vertical asymptote is at x equals what? What kind of 2 though? It's -2. Okay. And then lastly is 4. It's just identifying our horizontal. That's going back to our degrees, where our degree is greater than, less than, or equal to. Equal to. And what did it say you do if they're equal to? The A over B. You're leading what? Coefficients. So if there's no 1 here, it's Casper the Friendly 1. And then this one is 3. So where's our horizontal? 1/3. And you have now found all of your discontinuities. And I told you we could do it in under 5 minutes. We did. The bell didn't ring. We did it under 5 minutes. We did it in under 5 minutes. All right, so this is where we'll pick up tomorrow. Thank you for a great day. All right, here we go. So, yesterday I guess we've been doing this for a minute. We are talking about finding our discontinuities, right? And so we went through the steps of finding your discontinuities. Step 1, we factor the numerator and denominator. Step 2, we look for values that are zeros of both numerator and denominator. That tells us our wholes. Step 3, we look for values that are zeros of the denominator, and that tells us our vertical asymptote. And step 4, compare the degrees of the numerator. All right, guys, at this time, you don't need your computer. If your computer is open, that tells me you're not paying me any attention. Okay, you should have your notes out. And there, that's it. Okay. All right, so, and then step 4 is comparing the degrees of the numerator and denominator, and that's going to tell us our horizontal asymptote. So, at the end of class yesterday, we left off with the I do, which is the one I worked through. So following those steps, the first thing I did was fully factor using my factoring techniques. Second, we look for what factor did they have in common, and that was x minus 2. When I set that equal to 0, that tells me where my pole is, okay? Step 3 is to look at what's left in your denominator. What variables are left in your denominator? And I'm left with x plus 2. I set that equal to 0, and that tells me my vertical asymptote, okay? It's an asymptote because your denominator cannot equal 0, right? Step 4 is then to compare the degree of your numerator to the degree of your denominator. And our degrees were the same. When your degrees are the same, that means you have a horizontal asymptote at y equals your leading coefficients, okay? Your leading coefficients are the numbers that are with the highest exponent. Your highest power of your variable. That's your degree. That's why it's degree 2 and degree 2 here. Okay. And then that's what we did. So we're going to do number 1 together, walk through the steps, and then I'm going to pause and give you about 6 minutes to do 2 and 3. Okay. At your tables. So we're going to do 1 together, and then we're going to pause, and you're going to do 2 and 3 at your table for about 6 minutes. Here we go. So number 1, first thing you want to do is to fully factor. Is this fully factored? No. This is difference of 2 squares. So to fully factor this, it becomes x over x minus 3 times x plus 3. Now is it fully factored?
We know that 9 is perfect square and x squared is perfect square.
And they're being subtracted? I mean, if you have 2 perfect squares being subtracted, then they factor out to being the square root of the first term plus or minus the square root of the second term.
No, I know, but like.
Anytime you see 2 perfect squares being subtracted, you should think difference of 2 squares. Yep. All right, step 2 is to identify any common factors. Do they have anything in common? No, so that means there are no holes. It literally looks like a space in the graph. It's really hard to see on larger graphs, but when you're drawing it, you put a space. I put a hole generally.
Like if you're doing a straight line, it's not.
On the table, just say error at that. All right, on 3, we're now going to look at what factors are in our denominator and set them equal to 0. Do we still have factors in our denominator? Yes. So we're going to set each factor equal to 0. So when I set each factor to 0, the value that I get for x, those are my vertical asymptotes. So where do I have vertical asymptotes at?
3 and -3.
3 and -3. X equals 3, x equals -3. Okay. Step 4 is going back to the original and comparing the degrees of your functions. I mean, of your numerator and denominator. What is the degree of my numerator? 1. It's Casper the Friendly 1. If there's no power, then the power is 1. What's the degree of my denominator? 2. So we said when the degree of your numerator is less than the degree of your denominator, what does that mean?
It's a whole x equal a.
At y equals 0. If there's a horizontal asymptote at what? Yes, as we wrote in our notes yesterday. I don't know. I use a different set of notes this year, and they use M and N. I usually use N and D. You can switch it if it bothers you. They're your notes. At y equals 0. So these are our discontinuities. Vertical asymptotes and a horizontal asymptote.
Can there be 2 vertical asymptotes?
Yes, you can have 2 vertical asymptotes, but only 1 horizontal. Or no horizontal, or no vertical.
So if the, wait, but isn't the denominator in this one bigger than the numerator? Because it's 2?
Yeah.
Oh, it's in a denominator. N is denominator? I thought N was numerator.
So yesterday in our notes, we defined it. The degree of the numerator is going to be m. The degree of the denominator is n. If m is less than n, it's a horizontal asymptote. If m is greater than n, you have no horizontal asymptote. And if m equals n, you have a horizontal asymptote at your coefficients. Okay. All right. So I'm gonna put 6 minutes on, and you're gonna do 2 and 3. So we will check back at 9:48. All right, so on number 2, the first thing is you should have factored it. When you factored, rule number 1 of factoring is always check for a GCF, right? Greatest common factor. Is there a greatest common factor?
Yes.
Yes, you should have factored out the 6 first. Okay, after you factor out the 6, you're left with difference of 2 squares. So you have 6 times x minus 1 times x plus 1 all over x minus 1. Okay, step 2 is to ask yourself, are there any common factors? And the answer is yes. What is my common factor? X minus 1. So I'm going to set that equal to 0, and I get x equals 1, and that's where my hole is. So I have a hole at x equals 1. Step 3 is your vertical asymptote. When I remove this, is there anything left in my denominator? No. So then therefore there is no vertical asymptote. Okay. Step 4 is going back to the original problem and comparing the degrees. So the degree of the numerator is 2. The degree of the denominator is 1. So since the numerator is greater than the denominator, that means that there is no horizontal asymptote. The numerator is greater than the denominator? We discussed that already. I followed someone else's note.
I know.
Alphabetical order. Yeah. Guys. All right, here we go. So the only discontinuity here was a hole. Okay. On 3, it is already fully factored. There's no GCF. There's no difference of 2 squares. There's no simple trinomial. It is fully factored. Step 2, do they have anything in common? No, no holes. Step 3 is your denominator. And is there something in my denominator? Yes. So I'm taking 3x minus 2, but plus 2 and setting it equal to 0. So 3x plus 2 equals 0. I end up with 3x equals -2. So x equals -2/3 is a vertical asymptote. Okay. Step 4 is your horizontal asymptote. Comparing the degrees. Our degrees are going to be the what? 1 and 1. They're the same. So m equals n. So y equals your leading coefficients. What are my leading coefficients? 4 and 3. So y equals 4 over 3 is our horizontal asymptote. Yes. Okay. And that is what you should have gotten for 3. All right. So for part 2 of our notes for 3.5C, it is now putting it all together. Okay. So we broke down and took our time to practice identifying holes and asymptotes. That is its own step in part 2. Okay. What's new here is identifying your x and y intercepts. Okay. So finding your x and y intercepts. So to find your x-intercept, I'm gonna put a little line here. To find your x-intercept, you're gonna take the factors of your numerator and set it equal to 0. That's how we find our x-intercepts.
Did you make a line from step 2?
Yes. To find your y-intercepts, you're gonna plug in 0 for all x's. So wherever there's an x, you're gonna plug in a 0. Because we already know how to do step 1, identifying the holes and asymptotes. Step 2 is going to be the new piece. All right, are you ready? So we're going to do step 1 kind of fast. Step 1, identifying your holes and asymptote. This is already fully factored, correct? All right. So then I'm going to check for holes. Are there any holes? No. Now I'm going to check for vertical asymptote. Vertical asymptote depends on the denominator. So I'm going to take x plus 1, set it equal to 0. So where's my vertical asymptote at? X equals -1. I'm going to check for horizontal asymptote. Your horizontal asymptote depends on your degree. Are our degrees the same? Yes, degrees are the same. So therefore, it depends on our leading coefficient, and the leading coefficient for both is what? 1. So our horizontal asymptote is at y equals 1. Step 2 is to identify your x and y intercepts. So we're going to find our x and y intercepts. To find your x-intercept, you're taking your numerator and setting it equal to 0. So what's x? X equals -3. So our x-intercept is at -3, comma 0. How do you feel about finding the x-intercept? Good? Yes? Okay. Your y-intercept. So to find your y-intercept, it says you're plugging in zeros for all of your x's. So wherever there's a x, it becomes a 0. So we end up with 0 plus 3 over 0 plus 1, which gives us 3 over 1, which equals 3. Because it's a y-intercept, it's going to be 0, comma 3. Was it terrible finding x and y intercepts? All right. Questions over 1 and 2 so far? None? No? Sure. All right. So we're going to do our y-intercept. We're going to go ahead and put our asymptotes and our points that we have already. So I have a vertical asymptote at x equals -1. I would normally do a dashed line, but so that you can see where I'm at, I'm going to highlight it. We have a horizontal asymptote at y equals 1. Nope, that's reciprocal functions. We have our x-intercept at -3. And we have our y-intercept at 0.3. So step 3 is to graph what you already have. Check. Step 4 is to create a table to find other values. If you are comfortable with where you're at already, so we have -3, 0, we have 0, 3, and you feel good about sketching it out, you can. But all you're doing is choosing values around here and plugging them in. So we've already did 0. Could I plug in 1? Yeah, so I can find 1. When I'm plugging in 1, that means that wherever x is, I'm plugging in a 1. Does that make sense? So it would become 1 plus 3 over 1 plus 1. What does that give me? 4 over 2, which is 2. So the value at 1 is 2. I go to 1. I'm going to go up to 1, 2. Okay, we're going to choose a point to the left or to the right of this one. Doesn't matter which one. I'm going to go with -2. It could be any point around them. So as long as it's not your asymptote. Mhm. Okay, if I plug in -2, I get -2 plus 3 over -2 plus 1. And I get what? -1. So at -2, it goes down to -1. And that's plenty of points. You just need another point to like kind of follow your, help you guide yourself out. Okay, so from here, you should be able to define your domain and your range. Your domain goes from left to right. If I'm going all the way to the left, where do I start? -infinity. And what causes me to stop? My asymptote. So I stop at -1. I continue from -1 to infinity. And this is because x cannot equal -1. On my range, what's going to stop it? Your horizontal asymptote, right? So y cannot equal 1. So therefore, your range is from -infinity to 1, 1 to infinity.
Yeah.
All right, so that's the full goal of this section, is to be able to do it all. To be able to identify your asymptotes, find your x and y intercepts, create a graph, and find key points to help you finish out your graph. Okay? What are your questions, comments, or concerns? It can be. It looks like it. But just remember, the math is simple. Just the
It's like this job, especially with finding like the whole math and code, like, you have to remember like, oh, you're looking at this part of the equation and then.
yes.
That's the thing.
I don't have a secret to tell you how. I don't know. I wish I did, but I just remember it. So, all right. So the last part are just for you to practice. Key thing to remember when you're practicing here is that you make sure you use difference of two squares, right? On this one, remember, guys, real quick, you're asking yourself what multiplies and what adds to fully factor that, okay? All right. All right, so you should have done your we do practice, and now we're going to check and see how you process the we do really quick. So going through the steps, it says that we want to make sure that it's fully factored. This is an example of difference of two squares, right? I have two perfect squares being subtracted. So anytime I see that, I should think difference of two squares. So we end up with 4 over x minus 3 times x plus 3. Okay. From there, we're going to determine what are our holes, vertical asymptotes, and horizontal asymptotes. So first, looking at our holes, is there anything that eliminates? No. So there are no holes. Okay. Vertical asymptote. Your vertical asymptote depends on your denominator. And our denominator, we have x minus 3 and x plus 3. So I have x minus 3 equals 0, and we have x plus 3 equals 0. So where are our vertical asymptotes? At -3 and +3. Okay. Next is our horizontal asymptote. Your horizontal asymptotes depends on the degree of your numerator and the degree of your denominator. Okay. The degree of our numerator, I'm going to actually use n so that you guys be happy. The degree of the numerator is actually less than the degree of the denominator. And what happens when the degree of the numerator is less than the degree of the denominator?
It's a 0.
It's at 0. Your horizontal asymptote is at y equals 0. So those are my discontinuities. So as far as it goes, I'm going to highlight 1, 2, 3. So I have a vertical asymptote at -3, a vertical asymptote at +3, and a horizontal asymptote at 0. Okay, so notice how, yes. Yep. So example 4, if you did it, notice that this time, instead of just having one vertical asymptote, you actually had 2. So what that means is that there are 3 different shapes occurring on this graph. Okay. Next, we're going to find our x-intercepts. Are there going to be any x-intercepts? The answer is no. Why can there not be any x-intercepts? There's an asymptote at 0, right? So there's no x-intercepts. Can there be y-intercept? Yes. How do we find our y-intercept? We plug in 0 for x. So everywhere there's an x, we plug in 0. So we have 4 over 0 squared minus 9, which is just 4 over -9. So our intercept is going to be at 0, -4/9. Ooh, I like how that 4 looks. Yeah, I like it. This one right here. Yeah, turned out decent there. All right, so my y-intercept is right here. How did we get what? So your y-intercept, we said that you're plugging in 0 for x, and 0 minus 9 is -9. So my answer is just 4 over -4/9. That's my y-intercept. That's it. All right, so what happens here, this tells me, we're not going to draw it perfectly to scale. We're going to also look at it in the calculator. But this tells me that my graph is following the asymptotes this way, in the middle. So in the middle, it is following the asymptotes like so. Because I can't cross, so I must be going down, right? I can't have that horizontal, so I can't go up. I must be going down. It sets a boundary for me. Okay? To figure out what's happening on your left branch and your right branch, that's where you create the table to figure out those values. So I'm gonna, you also can do it on the calculator. We can do it really quick by hand though. So right here, I'm at -3. To the right of -3 is -4. Here I'm at +3. To the right to the right is going to be +4. If I plug -4 and +4 into my original equation, what's going to happen? So we have 4. And then we have -4 squared minus 9.
Don't we have to correct for? What's the word? 4/7?
I'm listening.
So when I put it in the calculator, the spot where it has error in the table, was that like?
Those are our asymptotes. Your error can be a whole gap or asymptote. And for our errors, error on the calculator can be a hole or an asymptote. Any type of discontinuity is going to create an error. You have to be able to calculate. So did we have a hole here? No. So therefore, those errors are our asymptotes. Okay. So, who just talked to me? Z. He said 16 minus 9 was 7. So we had 4 over 7. The same thing's going to happen at 4, right? Because the negative is going to be the same effect. So it's also going to be 4 over 7. So we know that our graph is doing this. It starts somewhere in here, and it's just going to follow the asymptotes. Follow the asymptotes. And it's going to mimic it on the other side. Follow the asymptotes. I followed it too well there. Okay, so we're going to look here and talk about our domain. So your domain here has how many things that it cannot equal? Your domain has 2 things, right? It cannot equal -3 and it cannot equal +3. Do we see that? Your range cannot equal just 0. So on your homework, it wants you to go back to writing your, I think it's gonna probably ask you to write it as inequality also. So when I'm writing this as an inequality, this is saying that your x is less than -3, right? Because that's to the left of -3. Does that make sense? Okay, the middle, if I'm in the middle, that's telling me that x is between -3, that's a weird, -3 and +3. And if I'm on the right, it's telling me that x is greater than 3. Does that make sense? So reading from inequality, this happens to the left, which is less than a -3. This happens between, do we see? This happens between -3 and +3. And this happens to the right or greater than 3. Okay. And then for your y's happen everywhere but where? At 0. So your y is either going to be greater than 0 or less than 0. Or y is less than 0. But will it ever equal 0? No. Okay. So you got to be comfortable reading what's happening on the graph. And again, it's all based off of left to right, middle, center, and going from there. Okay. If you put this in the calculator, this is what it'll look like. Did anyone actually graph it to see the funness? Yeah. Yeah. The only thing is that you don't see the asymptotes because you put the 4 over x squared minus 9.
So it's just gonna have that little like. That,
Mhm.
so it's not gonna have the highlight.
No, it doesn't show you your asymptotes.
Is there a way to, like, after the
Mm-mm.
errors?
That's why you have to be able to do it manually.
Let's see. Well, so you can look for the errors, right?
You just gotta know if the error is an asymptote or a hole.
So it's, like, can you have 3 errors, so it's like a whole asterisk?
Mhm.
So you should figure out which
You have to
one.
know which one they are.
So you could just look at the table, look at the graph, and if it looks like this.
Yep,
Find out there's no hole.
all asymptotes. Yep. All right, the other one, this is another example of a unique rational when you graph. This one, we're gonna go straight to the calculator to graph. After we find our asymptotes, okay? So on here, this is an example of something you cannot factor. Do we see this? Because we ask ourselves, is there anything that multiplies to give me -2 but adds to give me a +2? And the answer is no, I cannot. This is fully factored, right? Because it's fully factored, when I describe my asymptotes, I know that there are no holes, right? My vertical asymptote depends on my denominator. So where is it at? 1, at x equals 1. And my horizontal asymptote depends on the degrees of my numerator and denominator. The numerator is greater than the denominator. So that means that there is no horizontal asymptote. All right, so let's talk about graphing this bad boy. When you're graphing a rational function, you want to make sure you put the numerator in parentheses and the denominator in parentheses. So I'm going to put parentheses, x squared plus 2x minus 2 divided by x minus 1. It's weird, isn't it? Okay. So let's look at this bad boy. It's coming in. It's like, oh, tricked you. Oh, there we go. Okay. This is a rational function with what we call a slant asymptote. Okay. It is not part of our curriculum to find the slant asymptote, but this is called a slant asymptote. No. You just have to be able to read the domain and range of what's happening here. Does that make sense? I'm not asking you to find slant asymptote, but you have to be able to read the domain and the range. Yeah, so I'm going to plot it out for you really quick. We have a vertical asymptote at 1. We know that mathematically, right?
Yes.
Because we already found that. And then when I look at the table to second graph to look at the table, I can plot some points to figure out everything else. So when I'm plotting my points, see at 0, I know that I'm at 2. At -1, I'm at 1.5,
Yeah.
right? And I don't know, at
2, you're at 6.
At 2, I'm at 6. 1, 2, 3, 4, 5. I can count. At 3, I'm at 6.5. So I can see where the graph is shaping out. So the graph is doing this. It's following my vertical asymptote, and then it keeps going, right? On this side, it's following the vertical asymptote, and it's going to keep going. But these values are doing what? They're decreasing. They're going down. Okay. And that's because there is a horizontal asymptote that's here. If you are trying to figure out that horizontal asymptote, you just do long division and you'll find that horizontal asymptote. Do y'all remember long division? And you would just do long division or synthetic and you would find it. But again, do we have to worry about that? No. Our goal is we have to be able to write the domain and the range. Okay. So we're going to describe our x's. What are our x values doing? So the only thing x can't equal is what? 1. X can't equal 1. Do we see that? The only restriction for x is x cannot equal 1. Other than that, x is either going to be less than 1 or x is going to be greater than 1. That's the only restriction for our x. Okay, our y's are where it gets a little different. Our y values have a different. So our y's on the left side, they go as high as what? What was this value? 2. So y's are less than 2. Or what happens on the left side? What was this value? 6. Or y is greater than 6. Now, because there are points there, it's not just that they're less than, they are less than or equal to or greater than or equal to, because they have value there. If I have value, I am equal. Does that make sense? Mm-hmm. If I have a discontinuity, I am strictly less than or greater than. Value makes me equal. Okay. The goal for this type of graph is to be able to define your domain and range, not to find the slant, but to be able to define the domain and range. What is your x and y doing? Got it? What are your questions about reading and finding the domain and range? None? We're okay? We see where x starts, x ends. We see where y starts and y ends.
What is value?
A value means that there's a point here and not an error. So at this y value, there's a value there, right? This is 2, comma, well, an x, comma 2, right? So therefore, that's why it's equal, not strictly less than. Yeah. But on our x's, we can't equal this. So therefore, it's strictly less than or strictly greater than. Okay? All right, that's the goal for graphs like this. On your test, you will have access to a calculator. Okay? At this point, we've practiced being able to graph and specifically identify. At this point, you will be able to graph in the calculator and you have to be comfortable identifying those attributes. Okay? Telling me the x-intercept, telling me the y-intercept, what's happening with your domain and range. Okay? All right, that is it for 3.5C.